Hello everyone. Today we'll be covering the part 2 of stoichiometry of CIE A-level or AS chemistry. In today's video we'll be covering the concept of percentage yield, which was also covered in your IGCSE years, and then the Avogadro's hypothesis for gases and the general complete hydrocarbon combustion formula and examples, and lastly the simple mass spectroscopy for your AS syllabus. Anyway, let's begin. So firstly, we'll start off with percentage yield. So in most of the calculations that we perform regarding solids, where we attain the moles and therefore the mass, you obtain a theoretical mass. Yeah. So let's say a very basic example actually. When you react magnesium with cold water, you will get magnesium hydroxide plus water. Sorry, not water, plus H2, hydrogen gas, right? Now, let's say, from your calculations, when you're given the mass of this and whatnot, from your calculation, you achieve that there is 1.1 grams of MgOH2 that you should obtain. However, in reality, because of many factors and impurities involved, the actual mass is less than the theoretical, or sometimes this is referred to as the calculated mass. Yeah, and the percentage yield is basically the percentage of these two. So theoretical divided by the actual, no, sorry, it's the other way around. It's actual divided by theoretical. And since it's a percentage, you have to times 100. And this will always be lesser than the theoretical or calculated mass. Okay, so let's take a basic example because this is very easy and it's something that you have covered in your IGCSE years. So for this reaction, C7 H6O3 plus CH3OH gives C8 H8O3 plus H2O. I think this is this is an esterification and condensation reaction, which will be covered later in your AS organic chemistry. And what you're given is that the mass of this compound obtained, the actual mass obtained is 31 grams. Now calculate the percentage yield. Oh wait, and another thing that you're given is that 7 times 12. This is the mass of this is 0. No, not 0. The mass of this is 50 grams, and this is an excess. Okay, so calculate the percentage yield. Okay, I hope you have attempted the question. If you haven't, let's attempt it ourselves. So first, because this is the limiting reagent, everything happens in accordance to this. Okay, so the moles of C7H6O3 is mass divided by mR, which will be mass is 50 grams, which is divided by 7 into 12 plus 6 hydrogen plus 16 times 3. And when you put that in the calculator, you should get 0.362 moles, right? And because this and this are in a 1-to-1 ratio, therefore the moles of the ester obtained is also 0.0, not 0.0, it's 0.362 moles. Yeah. Now from this you can calculate the mass of the ester. So mass of ester is the moles times the MR, which is 0.362 times 8 times 12 plus 8 plus 3 times 16, which would give you 55.1 grams. Now this is the calculated mass. This is the mass you're supposed to get. Now the percentage yield is basically, so what is the actual mass obtained? 31 divided by 55.1 times 100. So you should get an answer of 56.3%. I hope you understood. Next we'll be moving on to the concept of the Avogadro hypothesis and the complete combustion of hydrocarbons, like a general formula for it and calculations involving that. Okay, just give me a minute to erase everything. Okay, let's continue. So Avogadro's hypothesis plus gen formula for complete hydrocarbon combustion. Let's see, combustion. So from your IGCSE years, and something that will also be covered in your AS this year, you know that when a hydrocarbon undergoes complete combustion, it produces CO2 plus H2O when a hydrocarbon undergoes complete combustion, right? Now, what the Avogadro's hypothesis, which is basically a volumetric ratio, states that the ratio of gases is also the molar ratio. So for instance, let's say you have a common alkane, C2H6 plus O2, yeah, will give you what? CO2 plus H2O, okay? And you see there's 2 here, and then there's 6, so 2 divided by 6 would be 3, 2 into 2, 4 plus 3, 7 divided by 2, 3.5, right? So this is the molar ratio. It's 1, it's 3.5, 2, and 3. Now this, what the Avogadro's hypothesis states is that this molar ratio is equal to the volume ratio you would get if you were to perform calculations regarding the volume ratio. Okay. Now you may be wondering, why is this important? How exactly do we use this? Well, it's useful for finding out identity of unknown hydrocarbons. And the formula for complete combustion for hydrocarbon is CXHY plus X plus Y by 4 O2, which gives XCO2 plus Y by 2 H2O. This is an important formula, and I suggest you note it down and remember it for your convenience, as it's not mentioned anywhere in the data booklet. And this formula is what you'll be using to find out or determine the identities of unknown hydrocarbons, yeah? And the derivation of this formula is not required. All you have to know is the formula and how it should be used, okay? So let's take a simple example. First we'll take a simple example, and then we'll take a past paper question. So simple example, 20 centimeter cube of unknown at sea, unknown hydrocarbon, okay, and 120 centimeter cube of O2. Centimeter cube of O2 and 80 centimeter cube of CO2 is produced, all at RTP. So what is the identity of the unknown hydrocarbon? Okay, pardon that. Okay, why is it moving? Okay. Okay, I hope you've given an attempt at this question. If you haven't, let's proceed. So first you write down the general formula plus x plus y by 4 O2, which gives you XCO2 plus y by 2 H2O, right? And it's all at RTP. RTP means 24 degrees Celsius, right? So water will be in liquid state, not in gaseous state. So there's 20 centimeter cube of unknown hydrocarbon and 120 centimeter cube of oxygen. Well, they don't mention that oxygen is in excess, so we just assume that it is not. And 80 centimeter cube of CO2 is produced. Now, using the Avogadro's hypothesis, what you know is that the ratio of these volumes are also the molar ratios. So it's something like, so 20 is the lowest here, so everything gets divided by 20. So 20 divided by 20 is 1, 120 divided by 20 is 6, and 80 divided by 20 is 4, right? So this is also the molar ratio according to the Avogadro's hypothesis. So from this, you know that, so x here, so x becomes 4, therefore the identity of y would be x plus y by 4 is equal to, and what's the molar ratio of oxygen? It's 6, right? So when you make y the subject of the equation, so 6 minus 4, x is 4, so 6 minus 4 is 2, therefore y is 4 times 2, 8, right? And therefore the identity of the unknown hydrocarbon is Cx, so C4Hy8, which is I think butene. Now where the double bond is we do not know, but the identity of this unknown hydrocarbon we determined by the Avogadro's hypothesis. Now let's move on to a past paper question that I got. I don't know the exact year of this, but let's give an attempt. Okay, if you want to, feel free to attempt this yourself first by pausing the video at the correct times. Anyway, we'll begin solving. So first question, define the term mole, right? So mole, and define the term mole, so singular, so it's singular. So what is a mole? The primary formula or the primary idea behind the mole is the amount of substance, right? So N is equal to N by Na, the amount of substance that is in comparison to like the Avogadro's constant. So because we're defining the term mole, so assuming 1 mole, so what would 1 mole of a compound or a substance be? The amount of substance containing 6.02 into 10 to the power 23 particles of this substance. Yeah, you could, instead of writing 6.02 into 10 to the power 23, you could just say Avogadro's constant number of particles, but it's better to be more specific. So we'll move on to the main part of the question. Okay, so 10 centimeter cube of gaseous hydrocarbon CxHy was reacted with 100 centimeter cube of oxygen gas, and excess, so you cannot use this in the ratio yet. So the final volume of the gaseous mixture is to 95 centimeter cube. So this could either be the excess oxygen, carbon dioxide, and water, or just the excess oxygen and carbon dioxide, depending on the conditions. So the gaseous mixture was treated with concentrated aqueous sodium hydroxide to absorb the carbon dioxide present. So carbon dioxide is acidic and reacts with a base, right? This reduced the gas volume to 75 centimeter cube. Now the 75 centimeter cube can either be the excess oxygen and the water, or the excess oxygen only. By water here I don't mean liquid water, I mean steam. Anyway, all gas volumes are measured at 298 kelvins and 100 kPa, right? So what is 298 kelvins? How would you convert? So it's 298 minus 273. which is 25 degrees Celsius. So at 25 degrees Celsius, water is in liquid form because its boiling point is 100 degrees Celsius. So this is purely oxygen, the excess oxygen. Okay, there's oxygen remaining. So an equation for the reaction between sodium hydroxide and carbon dioxide. Now this equation is not given in your syllabus, however you can sort of guess the answer. So sodium hydroxide plus an acid gas, right? So when an acid and a base normally reacts, a salt is formed and water is given off. So NaCO. So an appropriate salt that could be formed is sodium carbonate plus water. And the reason why I say sodium carbonate is because there's a carbon dioxide here. Okay. So calculate the volume of carbon dioxide produced by the complete combustion of the hydrocarbon. So the volume of carbon dioxide, well, that is whatever was initially present, so 95, subtracted with the volume of carbon dioxide that is absorbed by the sodium hydroxide, so that is 75. So 95 minus 75 would be 20 centimeter cube. So 20 centimeter cube of carbon dioxide was produced. Calculate the volume of oxygen used up in the reaction. So you know that there's 75 centimeter cube remaining. And what was the initial amount that was used? 100. So 100 minus 75 would give you 25 centimeter cube of oxygen that was used up in the reaction. Okay. Now use your answers in use your answers in B1 and B2 and B3 together with the initial volume of hydrocarbon to balance the equation shown below. So we'll do this on the side, okay, to get more working space. I believe we need that more working space. So write first the general formula, Hy plus X plus Y by 4 O2 gives XCO2 plus Y by 2 H2O, right? And the x and y here is not respective to this equation. This is just simply constructing a general equation. I hope that makes sense. So what are the volumes? What is the volume of this? The volume of this is, I believe it was 10, right? And the volume of oxygen that was used up was 25 centimeter cube, and the volume of carbon dioxide given off 20 centimeter cube. So this is the smallest, so the ratio would be 1 is to 2.5 is to 2. We don't need a ratio for water for this question, I assume. So when you do that, you see that x equals to 2, therefore y would equal to, so that's 2.5 minus 2, 0.5 times 4, that's 2 as well, right? So y would equal to 2, x would equal to 2, and therefore the equation would be C2H2 plus x plus y by 4, that's 2.5 O2, which would give you XCO2 2CO2 plus y by 2 H2. What's y? Y is 2, so y by 2 is 1 H2O. Well, since it's 1, you don't write it. And therefore, now you bring this equation here. So what is the coefficient here? Which is x, so it's 1, right? For O2, it's 2.5. And for carbon dioxide, it's 2. So x, what is x? X is 2, right? C2, and y is also 2. And what is z? Z is H2O. So for H2 we only have 1, so Z is 1. Okay, I hope that makes sense. Next we'll move on to the last part of this lesson, which is a simple mass spectroscopy. So in your A2 syllabus, mass spectroscopy is used to identify organic compounds, but in your AS, it is just to find the AR of a AR or sometimes the MR of a substance, depending on the question, and also to find out the exact mass of an isotope. Okay, mass spectroscopy. So in the periodic table, for instance, Mg, I think 12 and 24, right? That was, I believe that is the AR for Mg. This AR is an average mass. And what is it an average mass of exactly? It is the average mass of the isotopes of Mg, the naturally occurring isotopes of Mg. This is the average mass that we use always. And how do we exactly calculate this average mass? We calculate this average mass using two values: the mass of isotope, yeah, and its relative abundance. That is how we calculate the average mass of which is basically the AR of Mg in this case. And for that we use the concept and the idea or the principle of mass spectroscopy. The diagram or the working principle of mass spectroscopy is not in your syllabus. However, if you're interested in learning how it works, you can look up a video on YouTube. But it basically involves ionization using electromagnetism. Anyway, so we'll continue. So how exactly do you find the average mass or the AR of Mg in this case? So assuming that Mg in general form is X, so the AR of X would be calculated. Wait, before the AR of X would be calculated by mass 1 times relative abundance 1 plus, okay, mass 2 times the relative abundance 2 and so on, divided by 100. And this is an important formula that you have to keep in mind and should be able to use from time to time. Okay, so because this formula is very straightforward and the questions from this topic in AS is very straightforward, we'll directly jump into a past paper question instead of wasting our time with example questions which are easy. So gallium is present in group 13. Okay, so it's in group 13. Sample of gallium is analyzed using a mass spectrometer. The mass spectrum is shown. So the first question is explain what is meant by the term relative atomic mass. So it is what the average mass of an atom of an element relative to 12 grams of carbon 12, where 12 grams of carbon 12 is 1, right? And then the next question is what is of interest in relation to the mass spectroscopy. So calculate the relative atomic mass of gallium in the sample. Give your answer to 4 significant figures. Show you're working. How exactly would you do that? Well, using the formula I mentioned before, AR would be, so what is the mass given? So mass is 69 times the relative abundance of that 69, so which is 60.11 plus 71 times 39.89, and this whole thing is divided by 100. And what would the answer be? So in your calculator, when you plug that in, 60.11 plus 71 plus 39.89, no, 71 times 39.89 divided by 100. 4 significant figures, the answer would be 69.80. This is the 4SF. The actual answer is 69.7978, right? So 69.80. 2 4 significant figures. Oh, and one more thing that is important when it comes to mass spectroscopy and calculations involving that. Sometimes they'll give you unknown natural like unknown abundances. Okay, so what you must know and what you must keep in mind is that the relative abundances always, like the sum of relative abundances, is equal to 100% always. So in this case, 60.11 plus 39.89 is equal to 100%. It has to equal to 100%. So whatever calculations you do, and if you have to ever determine or deduce the relative abundances, the unknown relative abundances, sometimes you have to use this concept. Wait, no, not this. This one, the sum of relative abundances is always equal to 100%. I hope you understood. If you do have any doubts, please leave them in the comment section below. And yeah, that is all. Please subscribe and like the video if we helped you in any way.